We'll proceed in innovative approach in calculus. We are talking about Lagrange. We are talking about Lagrange multiplier. Lagrange multiplier. And we are trying to find substitute, means different approach, rather I would say innovative approach through directional derivative along a particular vector. Directional derivative along a particular vector rather than going with Lagrange multiplier. The reason why we are saying this is because Lagrange multiplier is a case where we do maximization, minimization. Maximization, minimization along a constraint line. If we are talking about along a constraint line, then constraint line is x-axis when we go and calculate the maximization, minimization. Maximization, minimization, it happens through derivative only. This is the traditional way and the most proven way. If we want maximization and minimization in algebraic equation, then the best way is to calculate the derivative. Then equate the derivative with 0 and try to find out the value for the independent variable, at what independent variable this derivative tends to be 0. At that point, it can be these points are called extreme points, and at those points it will be typically maximum or minimum. This is the traditional way. Like like if I have x-axis, if this is x-axis, and if I have a curve like this, if I if I have a curve like this, okay, I have a curve like, okay, so this is a curve, and this is x-axis. Now curve is becoming minimum here and becoming maximum, that you can see. Now this is minimum and maximum with respect to x-axis. This is what we are saying. This is minimum or maximum with respect to x-axis. Now, now same thing what we are seeing, maximum or minimum. Now I'll hold it a little bit. Now if axis is here, then certainly this is not the maximum. This is maximum. If axis is here, then this is not maximum. This point is maximum. If axis is exactly like this here, then this is maximum from the distance. So maximum and minimum is a relative concept. Maximum and minimum is a relative constant. It is not a kind of a absolute term. If that is the scenario, then maximum minimum when we calculate, then if I'm uh, against which axis are you trying to calculate maxima or minima? Anyone would ask. Against which axis? Against x-axis. What is your independent variable? Certainly it is x is the independent variable. What is your dependent variable? It is y. dy by dx equal to 0. Now find the value of x for which dy by dx equal to 0. And in that sense, then you will get maximum or minimum. Now, in the constrained maximization minimum, this is what we are saying actually. Lagrange is nothing but constrained minimization maximization. In constrained minimization maximization, the axis against we are trying to calculate the maximum or minimum is or not always x-axis. X-axis is nothing but a line. Equation is y equal to 0. That is the x-axis. But this y equal to 0 can be any line. Like in our example, we took productivity of a company. If you watch our previous video, a company has productivity, and productivity of a company means company is manufacturing some product, and product needs two raw material. One is A raw material, type of A, and one is type of B. A is in X amount and B is in Y amount. X, someone has put X, A raw material in X amount. X can be number of items and B in Y amount. Y can be number of items. Now productivity is X to the power 2 by 3, Y to the power 1 by 3. If someone set this formula, then productivity of a product equal to raw material of type A in X amount, raw material of type B in Y amount, X to the power 2 by 3, Y to the power 1 by 3. That is the productivity. When it will be maximum? The answer is it will be maximum when X is infinite and Y is infinite. But there is a constraint line. Constraint is that the company is purchasing raw material of type A and B and raw material purchase cost is limited. In that way, if X is the amount of A and Y is the amount of B and per item is cost alpha dollar for X and for Y it is beta dollar per item, the net purchase amount is alpha X plus beta Y, alpha X plus beta Y equal to whatever the amount. So net amount is alpha X plus beta Y. That much company need to spend to purchase the raw amount. And then it manufactures the product and productivity equation is X to the power 2 by 3 into Y to the power 1 by 3. What it means? It means that productivity is more dependent upon X than Y. Now, the purchase cost is limited in the sense that alpha X plus beta Y must be less than equal to 3. This is what we are saying, must be less than equal to 3. If that is the case, 3 means $3 million, $3,000, $300, $3, whatever. If that is the case, now consider alpha and beta are 1, 1. Means in a simple case, now it is x plus y less than equal to 3. If I take a constant line at x plus y equal to 3, because whatever equation we are seeing, x to the power 2 by 3, y to the power 1 by 3, this is actually three-dimensional, where x and y are independent component and productivity is z-axis. X to the power 2 by 3, y to the power 1 by 3 is X is independent component, Y is independent component. XY plane is independent component. Productivity is Z or function over X and Y. Now Z at origin when X is 0, Y is 0, productivity is 0. But as X and Y increases, productivity increases. So there is no chance, there is one minimization we can see at the origin. Beyond that, there is no chance that it will hit any extreme point below the x plus y equal to 3. So x plus y less than equal to 3, we are taking the constraint. So below the x plus y less than equal to 3, for the x and y, please watch previous video for detail. So below x plus y less than equal to 3, there is no chance that it would attain any local maximization or minimization. It will keep on growing. So we have to find at the line x plus y equal to 3 that where on this line it will hit the maximum value. Because if this is x-axis, if this is x-axis, this is x-axis, this is y-axis, then this line is x plus y equal to 3. Along this line x plus y equal to 3, any moment the z value can reach the maximum. Means now the idea is in the domain. So if I have xy plane, if I have xy plane, in the xy plane, this is x-axis and this is y-axis. X-axis, y-axis, z-axis. Z-axis is the productivity. Now, if this is x-axis and this is y-axis, then this line is x plus y less than x plus y equal to 3. We are trying to find x and y points below this line toward the center in this region. But we know that in this region, if I take x and y, the fxy x to the power 2 by 3, y to the power 1 by 3 keeps on growing. Z value keeps on growing. So above this xy line, the z value if I take somewhere, it will be maximum, somewhere it will be lower. But it will be certainly bigger than the lower side of the x plus y equal to 3. Okay, so if this line is x plus y equal to 3, this is x axis, this is y axis, this is x plus y equal to 3, then this lower side, here there is no, here it will certainly z value will be lower. As we grow in x and y, z value will be bigger. On x plus y equal to 3, that is the constant. We cannot go beyond it. So on here only some point the z value will be, this is xy plane, z value will be maximum, that we need to find. We are trying, so Lagrange is way is lambda way, that we have seen. Lambda way is that if I draw a contour line, so in contour line the we have equation x to the power 2 by 3, y to the power 1 by 3 equal to the productivity. So productivity, if I take constant, any constant, then I can draw set of point on xy plane for which that it meets the constant, like x square plus y square equal to 1. Then if I say what is x and y, x and y will be set of points, not one point. If I say x square plus y square equal to 1, if I say x equal to 1, y equal to 1, then net output will be one number 1. But if I say output is 1, x square plus y square equal to 1, then there will be set of x and y point that will satisfy x square plus y square equal. That point is a circular, that point is a parameter of a circle. That's why it becomes a circle. That is another way of looking at the circle. If that is the sense, then x to the power 2 by 3, y to the power 1 by 3 equal to productivity. If I keep changing the productivity, then for each value, that is the contour diagram, I can draw a diagram on the xy plane. And there will be a time when if I keep growing this contour, it will start touching x plus y equal to 3. So if this is the xy plane and this is x and this is the line, that is x plus y equal to 3, or this is x axis, this is y axis, this is x plus y equal to 3. If this is the contour, if I grow the contour one time, it will start hitting. So initially contour is small, initially contour is smaller, then contour is bigger. This is the origin. Contour is bigger, contour. One time it will start hitting this line. The moment it starts hitting this line, at that moment the gradient of this curve that will be perpendicular to the curve and gradient of this line that will again perpendicular to the line, both will be parallel to each other, and then we can satisfy them as equal. So gradient of the algebraic equation for a contour, okay, equal to lambda into gradient of the constraint line, because they are parallel to each other, only difference is the magnitude. This is what Mr. Lagrange is saying. Then find out the value of x and y. But we are going through the traditional way of, I always advocate for the primitive calculus, always. Primitive calculus is the actual calculus. So traditional way of calculating maximization and minimization, the traditional way of calculating maximization and minimization is always dy by dx equal to 0. Now here, if I take the productivity equation for a contour x to the power 2 by 3 y to the power 1 by 3 into y to the power 1 by 3, if that is the algebraic equation, then its derivative, first I have to find the derivative, and when I find the derivative, then I have to find, equate it to 0. Okay, then I have to equate it to 0. So now let's go by the contour fundamentals only. If I go by contour fundamentals, then x to the power 2 by 3 into y to the power 1 by 3 equal to some constant. Then y equal to constant into some x to the power, I believe y to the power 1 by 3 equal to constant x to the power minus 2 by 3. That is the equation it comes, or y equal to constant x to the power x to the power minus 2. Means this forms a two-dimensional algebraic equation. When this y will be maximum dy by dx, but this maximization we are doing along x-axis. This maximization we are doing along x-axis. but we have to do maximization along another axis that is found by x plus y equal to 3. X axis means y equal to 0, y equal to 0. dy by dx equal to 0, we are trying to find extreme points along the y equal to 0 line. This is what we are trying to do. But we have to find the extreme point along line x plus y equal to 3. As I say, if someone asks if this is x-axis, this is x-axis, then what is the maximum point anyone see? This is the maximum point anyone see. Perfect. If this x-axis is like this, if this axis along which we are trying to calculate the maximization, minimization, if this axis is like this, then what is the maximum point? Certainly this is the maximum point. If axis is like this, then this is the maximum point. If axis is like this, then this is the maximum point. Maximum minimum point is relative to the axis against we are trying to calculate the extreme point. Here also we are trying to calculate extreme points of the contour against axis is formed, that is x plus y equal to 3. This is our invention. Please support us. Plus 91 is India country code. 9483160610. 9483160610. This is the telephone number. Plus 91 is the India country code. Now we are molding this problem into traditional way of calculating the maximization minimization rather than introducing one lambda and finding the gradient vector in this way. Always better always to try find out something with minimum complexity, not going with a new variable and higher complexity. Now we are trying, so the traditional way is dy by dx. Dy by dx is nothing but the calculation of maximization, minimization of y, that is algebraic equation, against a vector that is I. The x-axis is y equal to 0, x-axis is y equal to 0 in algebra. But in vector, it is I vector. We are trying to find the maximization and minimization of fx, y along the vector I. If I find a vector of this x plus y equal to 3, then I can say I need to find the maximization, minimization of algebraic equation y against the new vector u. This is, then we are riding on the track of traditional maximization, minimization only. Nothing, no surprise. What is directional derivative of an algebraic equation along any vector u? Along any vector I, that is dy by dx equal to 0. Any vector u, that is dy by du equal to 0. If I have x-axis, that is I vector, then dy by di vector equal to 0. That is the way to find the maximum minimum along any axis x. Okay, maximum and minimum along any vector u, any axis x, or any vector I vector, any vector u vector dy by du equal to 0. U I have to take unit vector. Here if I is unit vector, u I have to take as unit vector. Okay, let's try calculating I'll take one real example. So I have to find the maximum minimum of algebraic equation x plus y. X plus y, this is 3D. Means if this is x-axis and this is y-axis, if this is x-axis, this is y-axis, then at any moment I have z value, that is x plus y. At origin it is 0, but as we go along in first quadrant where x is greater than 1 and y is greater than 1, then it will start rising. If I go in the second quadrant where x is negative, y is positive, it will be accordingly. If I go in third quadrant, it will below the xy plane because it will be negative. And fourth quadrant as per the x and y. Now, if that is the scenario, then consider that z value fxy or algebraic equation is x plus y, where it would be maximum. When x is infinite and y is infinite, it will be maximum because it is a rising curve. It is there is no local maxima or minimum. It is plain rising curve. If x is growing, y is growing. Maxima. If I am trying to find maxima, no. There is a constraint. Constraint is there is a line. there is a line called x square plus y square equal to 1. I'm not saying less than equal to 1. Equal to 1 means there is a circle on the xy plane. There is a circle on xy plane. You have to find maximum or minimum along the perimeter of the circle only. If this is the circle, this is xy plane, this is xy plane and circle is lying on the xy plane, then you have to find maximum or minimum only on this line. Not in this region, not in this region, only on this line. That is the constraint. Earlier we saw the company's productivity x plus y less than equal to 3. Here x square plus y square equal to 1. On the line only please find the maximum minimum, not in any region. Okay, that is the constraint. So as per the our fundamental directional derivative we have to find what is the kind of x plus y is the algebraic equation for which we have to find maximum or minimum along the line, that is perimeter of a circle x square plus y square equal to 1. So we have to find directional derivative of an algebraic equation x plus y along a curve, not along a line, along a curve. There is something called line integral. There is something called surface integral. We are trying to find directional derivative along a vector field. This is new thing. This is not available in calculus itself. Directional derivative is available in calculus. Directional derivative is available in calculus. Calculus against a directional derivative is available in the calculus against a vector. But here, can you see this vector against a vector is not, vector means a straight line. If I talk about vector, then certainly it is a straight line. If I have an algebraic equation, if this is the algebraic equation, I have to find maxima or minima along this vector, along this vector, along this vector. This is x-axis. Along this vector, this is y-axis. Like that. Now, this is there is some algebraic equation. I'm not saying x plus y whatever. But we are trying to find directional derivative along a circle. Going through Lagrange way is something like running away from this problem. Problem is simple. I want directional derivative along a curve, not along a straight line. X square plus y square equal to 1. Okay, along the curve means curve can be curve means we are trying to, but we have no possibility to find maximum or minimum along a vector. What is a vector for this curve? Everywhere vector for this curve is different. Here vector for any line, vector equation for any line I can draw. If I take any point on this circle, then vector representation is tangent to the circle. Vector representation is tangent to the circle. Vector representation is tangent to this. Every moment the vector representation is changing in the curve. So this is typical example of a vector field. Vector field, algebraic vector. Now constraint line or directional derivative along a vector, rather someone can present a paper now. Directional derivative along a vector, rather than we have to find directional derivative along a vector field. Please do support us. So we are trying to find directional derivative along a vector field. Vector field means vector where components are algebra. Vector means a vector whose components are numerical, that is static vector. Vector whose components are algebra is called vector field. Directional derivative of an algebraic equation against a vector field. What is directional derivative of an algebraic equation? Along any vector u, that is gradient vector of the algebraic equation dot product, vector dot product, and then the unit vector along the vector u. That is the directional derivative of any algebraic equation is y equal to fx dy by du. This is what we are saying. Now u is not a vector, u is a vector field because it's a circle, it's not a straight line. What is the vector field along the circle? If I take any point, this is our proof. But this is exactly on the track of the finding maximization, minimization. Because once we get directional derivative, I have to set it to 0. That's it. To get the maximum or minimum. Now, now I have a circle equation in x square plus y square equal to 1. Now I have to find the kind of vector field representation of this circle. If I take any point here x comma y, any point here x comma y, then the position vector is xi plus yj. If I differentiate it, then it will be tangent to the position. Everywhere position vector is like this. Then tangent, this is what we want. That is the vector. So what is the tangent vector for the position vector xi plus yj? Because any point can be represented as x comma y, xi plus yj, xi plus yj. What is y? Y is 1 minus x square square root 1 minus x square, xi plus square root 1 minus x square j. That is the position vector. If I differentiate it, I get the vector along which I have to find the directional derivative. Now it will be I minus x by square root of 1 minus x square j. Derivative of square root of 1 minus x square is minus x by square root of 1 minus x square. Or we can say I minus x by yj. I minus x y y j. This is the, can you see this is a vector field? First component is 1, I component is 1, very nice. This is numerical, this is static vector. But another component is minus x y y. That is algebra. This is not a normal vector. This is a vector field. Now, what about gradient vector for this algebraic equation x plus y? The gradient vector for algebraic equation x plus y is I plus j. I plus j dot. I plus j dot. Unit vector for this. Unit vector for this is I minus x y j x y y y j. Unit vector for this will be 1 square plus x square plus y by y square root. That I have to divide, set it to 0. This is what is the principle of finding maximum and minimum. Dy by du equal to 0. Now the denominator what we have set for unit vector, it will be set to 0. I mean I have I plus j, I plus j dot product with I minus x y y j divided by the magnitude. Now this magnitude will be set to 0, not required. Now it will become I and I. So it will become 1. Dot product will become 1 minus xy equal to 0. If that is the case, then x equal to y. Simple, right? So x plus x equal to y. This is not my way. This is the actual way to find the constraint maximization and minimization. We introduce that this is possible through the traditional way only. We don't need any invention of lambda or anything like that. X equal to y. If I can try with the Lagrange way also. Lagrange says that just calculate the gradient vector of both and set lambda. The gradient vector here is I plus j. I plus j. X plus y gradient vector is I plus j. Means, okay, someone can find. We have tons of videos on this gradient vector. I plus j. What about gradient vector for the circle x square plus y square equal to 1? 2i plus 2j. Now I plus j equal to lambda 2i plus 2j. This is what he said. I'm sorry, the gradient vector for the x square plus y square equal to 1 is 2xi plus 2yj. I plus j equal to lambda 2xi plus 2yj. If I say lambda, then it becomes 1 by 2x. 1 lambda, it becomes 1 by 2y. If that is the case, then 1 by 2x equal to 1 by 2y. X equal to y. Here also x equal to y. At the end, answer will be same. So this is something that is what we are doing is that we are molding it into traditional way to find the differentiation find the maximum and minimum. This is what we are trying. Okay, so I believe we can take more examples. So we are not kind of running away. So we will take more example, and we will take example in 3D also. Here everything is going on 2D. We converted the actual problem is in 3D. If I say my equation is x plus y, actually it is 3D. Our productivity of the company is x to the power 2 by 3 and y to the power 1 by 3. That is the 3D. Where constraint line we are drawing in xy plane means in 2D. This is what the constraint line. So we'll try to find in 3D if it is possible. Otherwise, we will see 4D example where constraint would not be a line, constraint would be a surface. You cannot cross this surface. 4D. This is also called density function, 4 dimensional. So those reasons we will try to find out that how we can proceed with the traditional way, Lagrange way. I believe it will not cross that limit. It is good for the 2D only where we set lambda. But the traditional way will go away, will go. If there is a traditional way to find maximization, minimization with respect to x-axis and y-axis or xy plane, then certainly we will be able to find it for the constrained surface also. Only difference is rather than x-axis, y-axis, we will have another axis. Otherwise, so it will become a directional derivative along a vector rather than directional derivative of x-axis, y-axis. So those things that we will see. Please do support us. +91 is India country code 9483160610.